So we've been working in the last few videos towards the idea of relating two categorical variables together. And the first test we learned to relate two categorical variables was called the chi-square test for homogeneity. And I referenced or kind of alluded to this in the previous video, but there's actually a second test that you also use when you have two categorical variables you're trying to relate. It's called a chi-square test for independence. So these are very, very similar techniques we're going to be talking about in this video compared to the last one. And in fact, the calculations that we make you guys do are going to be the same. It's the same calculator command. It's the same p-value stuff. It's all the same in terms of the math. The difference is going to be in what we actually say and do with the information we get mathematically. So let's go ahead and jump in. So we need to flash back all the way to chapter, we talked about this in chapter 4, chapter 1, chapter 3, beginning of the year stuff. So we're way back now in first semester, reviewing what it means for two variables to have an association with each other. The idea of having an association, remember that in statistics, talking about cause and effect is a very strong thing. Talking about cause and effect is something you should avoid doing unless you know for sure that you have that random assignment, which allows us to make those conclusions, blah, 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 all that stuff. When you talk about an association is like a lighter way of saying, hey, these variables sort of have something going on with each other, but you're avoiding saying this one affects this one, or this one causes this other thing to happen. So when two variables have an association, what we're really talking about here is that knowing the value of one. So knowing the value of one variable, that's going to give us information. So it gives us info about the value of the other. So notice how I'm dancing around that idea of this one affects this one. That's a very strong thing to say. But if two things have an association, they're connected in some fashion. We've seen tons of examples of that over the course of the year. So on the other hand, the opposite the polar opposite of having an association is being independent. When you say that two variables are independent, the definition we did first semester said that knowing the value of one gives you no info on the other. Or in other words, there's no association between your variables. So you can sort of think about having an association and being independent as essentially opposites. So we've got this idea of a chi-square test for independence. And when we're testing whether two variables have an association or not, the calculations, as I said earlier, are the same. We're going to do the exact same math we would do in a chi-square test for homogeneity. The difference is in how we interpret it. So in a chi-square test for homogeneity, the last stuff we were doing, you would have your different bubbles or your different treatment groups or your different samples. So for example, we did that Italian music, French music, no music, and we wanted to see if the distribution of entrees was any different for each of my groups. Were the groups the same essentially, or was there a difference perhaps caused by that music? So that's what we were going for with homogeneity. Homogeneity comes in when you have separate samples, so separate samples or treatment groups. So say I were to take instead a sample from our school and a sample from a different school, and I wanted to see if there was a difference in opinion about math or something like that, like how much you like math, what kind of math grades you're getting, something like that. Two separate groups. That's a test for homogeneity. In a problem with a test for independence, your data instead comes from one large sample. So let me help you understand that, because it is a little tricky keeping these two things straight here. When I think about a chi-square test for independence, I think about I just collected a bunch of data. I've got my big pile of data right here, and I'm sort of sorting through it and seeing what's going on. And I say to myself, I wonder if this variable and this variable in my data have any sort of connection to each other. Well, in that situation, my data came from one big pool. I might look to see if there's an association between two of my variables, and I would do a chi-square test for independence. Take the same scenario, but instead of like one big pile of data right here, I instead had some data from one school and some data from another school. And I wanted to compare those two separate piles of data with the same variables. Are these two variables different here than here? Well, then I would use a chi-square test for homogeneity instead. So separate samples versus one sample is a good way of thinking about that. Homogeneity, you have separate samples or treatment groups, especially in experiments. So when you're doing experiments, you're going to have your separate treatment groups, test for homogeneity. When you do independence, you collect data, and then maybe after the fact, you think about, I wonder if this variable has connections with this other one. If that's still fuzzy, that's okay. It'll make more sense as we kind of progress here. And even if it doesn't, I'm going to give you a workaround later on. So we talk about how the condition of like sampling is the big difference between our two chi-square tests for two variable problems. Remember, we also have that chi-square goodness of fit test. Goodness of fit is when you have one variable, like M&M color. That was it. So if you have one variable, that's a whole separate domain. But for these other two tests, homogeneity and independence, the work and the calculations and the conditions are pretty much the same. The one difference here, and it talks about this at the top, when you do independence testing, you have one sample, as it says right here. Whereas if you do homogeneity, you have two or more samples / treatment groups, but the conditions are essentially the same. So the way that you structure your hypotheses uses different wording depending on what kind of test you're doing. In the previous problems, we were talking about the difference in distribution between our groups. Well, we only have one group right here. We're just analyzing after the fact. I honestly think these conditions might even be easier to put in words. Remember, HO is always statement of no difference. No difference or status quo in a problem would be these variables have nothing to do with each other. So your HO, you say there's no association between your variables. These variables are not connected in any meaningful way. And then you look to see, hey, is there actually enough evidence that there is an association and we've got some sort of connection going on? So HO, no association between variables. HA, there is some sort of association. The calculations, all of this, exactly the same thing. No difference in how you calculate your test statistic. The calculator command's the same. The degrees of freedom are the same. You're doing the same math. You're just putting a different spin on how you interpret it. So our example problem for the day right here. So we collected this bunch of data here, 460 high school students, one big pile of kids. And we asked to look at their fingers, and we asked to see if there was a difference between the ring and the index finger for which one is actually longer. So we recorded whether the index finger was longer, whether they were the same, or whether ring finger was longer between all these people. Now, this data came from one giant sample. It's not like I took one sample of males and a different sample of females. And this certainly isn't an experiment where I'm randomly assigning something. These are signals to me that this would probably be a chi-square test for independence. Also, if you see the word association in the problem, that's almost always a dead giveaway that you're doing independence and not homogeneity. So I see I'm doing, chi-square for independence. I'm going to go ahead and write my hypotheses. So remember, your HO in this problem is going to be that there's nothing going on. So there is no association between gender and finger length. Finger length is a tiny bit imprecise. It's like whether your ring finger is longer than your index finger, but I'm going to be a little lazy with that. So, it says relative finger length. That's a great way to make it better. Gender and relative finger length in HS high school students. And then, so presumably this is 460, you would assume maybe it's all from the same school, but somehow they got a random sample of all high schoolers. So that's just great. We can apply it to all high school students, not just at this one school. HA would be that there is an association. Honestly, like I said, I think your hypotheses might be easier to word in these problems than they were in the homogeneity problems. So I've got that set up with my hypotheses. I would set up my alpha, and they do tell me in this problem I'm supposed to use 0.05, and then it would be condition time. Now remember, before condition time, you need that expected table. So that's one thing I would need to do right here. And I'll pause and come back with that. Show work on at least one of your terms, and find your expected counts for this problem. All right, so my expected counts are over here on the side. I shamefully copied these right off the calculator. Did not want to do those by hands, but it's a good idea to show work on at least one term, as I did right here. And then you check your conditions. It was one big random sample. Since we are random sampling this time and not randomly assigning, you do need to check the 10% condition. 460 is less than 10% of high school students, and all of our expected counts are at least 5. So with our conditions out of the way, it would be time to actually run our chi-square test for this problem. So we're moving on now to the do step. And you're going to throw your data into the matrix if you didn't already. And we are going to run for this problem a chi-square test for independence. So let's go ahead and do that. I've got my data in here. That's my expected counts that I copied. And when I go stat tests and I run it, it's the same calculator option. You would do the same exact math you would do with homogeneity. The difference is just in how we interpret it. Remember, it's not GOF. Goodness of fit is for a one variable problem. We do still have two. So we want the chi-square test, and you can calculate. Looks like our test statistic is 2.07 if you round. P-value is about 0.35. Degrees of freedom are 2. So let's see. We got 2.07. P-val was about 0.35, and there were 2 degrees of freedom. Again, that was going to be categories minus 1. So 2 going vertically, and then 1 going this way. 2 times 1 is 2 degrees of freedom. Now, quick comment here. If you're having trouble distinguishing between the two types of problems, oh, is this independence? Is it homogeneity? Don't say it. Just say chi-square test. Chi-square test is vague and may cost you on a rubric possibly. But if you're like, I truly have no idea, I'd just be guessing. Don't guess wrong. Just say chi-square test. But just from what I've seen on previous AP tests, they do tend to favor this one, the test for independence, over the test for homogeneity for whatever reason. So if you feel like, no, I really want to guess, if you're totally in the dark, guessing independence is maybe a little better. But if you're like, I just don't know, you could call it a chi-square test and stop there and hopefully not lose too much credit. So anyway, if you look at this right here, I think this is the first video in this chapter where it has not been convincing. I don't want to make you think it's always convincing evidence. In fact, it's, in my opinion, a little hard to get the evidence to be convincing for chi-square problems. And certainly there were some differences in these groups, but the differences weren't big enough for us to be blown away by it. So on this problem then, we would want to fail to reject HO. So since our p-value is way too big, it is far over our alpha, we're going to end up failing to reject HO. And if you think about what that means, what does it mean if I fail to reject HO? Are they independent? Is there an association? Is there not? You got to be careful in how you word this. First of all, HO said that there's no association. It would be a really bad thing for you to turn around and say, there's convincing evidence that they're independent. Hey, the variables are independent, okay? There's a big difference between saying we're not convinced there's an association. We don't know if there's anything going on. There's a big difference between that and between saying, hey, there's actually an association here. So saying we don't know or we're not convinced is not the same thing as flipping it and saying, oh, independence. There still could be something going on. The evidence just wasn't good enough. So when you'd frame this, frame it delicately, what I'm going to say is there is not convincing evidence for HA. And when you read HA in this problem, HA was that there is an association between gender and relative finger length. And I want to repeat what I just said a minute ago, again, just to make sure it makes sense now that it's actually on the screen and you can see it. Me saying, I'm not convinced there's an association. I'm not convinced there's a connection is way different than me saying these variables are independent. They're straight up not, like they're not related. Those are two very different things. So be careful when you do this. Convincing evidence for HA, not convincing evidence for HA. Don't turn around and talk about, oh, HO is true. That's a bad thing, okay? So just be very mindful of that. If you want to show things are independent, back in our conditional probability chapter, there was a whole formula. Probability of A equals probability of A given B, stuff you'd have to do. So be mindful of that. So last thing we need to talk about here is just kind of practicing with how you know which chi-square test to use, because now we have 3 of them. Goodness of fits, as I've said several times, is when you have one variable, like our M&M problem. Homogeneity is a 2-variable problem. You do have your 2 different categorical variables, but you have different groups, either different samples, or you did an experiment and you put them in different piles. Independence, you take one big pool of data and you look at the variables from there. So the wording is really the key difference between the homogeneity and independence problems. And then there's just that comment that I made earlier. Just say chi-square test if you're really in doubt on what you're supposed to do. So if you look at this data set right here, just to practice with what kind of test we're doing, we are looking at a table that contains people's ages and whether or not they use social networking. So those are our 2 variables, and both of those, are they categorical? If you look at somebody's age is totally quantitative. Age is a number. So you would be like, should I be doing chi-square here? Like, is this something else? But what makes it categorical, they didn't look at the actual number. They just put people into piles, little buckets based on their age right here. So you can take a variable that's numbers and you can break it into like chunks and make it a categorical variable, which is what's going on here. So they broke it into categories for that first one. Be mindful, you do have to do categorical data to use chi-square. All right, why is goodness of fit not appropriate? Well, we have 2 variables. We have age, or age group, and we have social media status. So if you have 2 variables, you can't do a chi-square goodness of fit test. Describe how the data could have been collected for a test of homogeneity to be appropriate. They didn't say in the problem, this same table right here, it didn't say where it came from. So we would word our problem differently if this was one sample or many. So what would have to happen for homogeneity to be appropriate? Well, it'd need to be separate samples. So what I would have to take all 18 to 24-year-olds and pull 183 of them. Then I would move and I would take a separate sample of 25 to 34-year-olds. Boom, boom, boom. Separate samples for each age group would be how that would work. So separate samples for each age group would make this a test for homogeneity. And then if you're looking for, well, okay, how would it be a chi-square test for independence? It would need to be one big sample. Honestly, that's what I think this probably was when you look at this problem. Picture an online survey where you're just asking people stuff. You probably didn't just ask them about this question. When you take like a poll or a survey on something, they've already got you there. They're probably going to ask you like handful of questions about different things. I doubt this was the only question on their survey. So what happens is, if you picture, they have like this giant spreadsheet where everybody's data poured in as they filled out the survey. And then they looked after the fact and they might have been like, I wonder if age and social media are connected. Oh, well, what about these other two variables that we looked at when we collected our data? If you go back after the fact and it was just one big pool, which is more common, you're probably doing a chi-square test for independence. That homogeneity type problem, though, is very big, especially with experiments. So keeping the wording and the scenario straight is a little bit tricky, but the math is the same. If you get tripped up on, which one is it? Just do your math and call it a chi-square test and just move on from there.